for generating the Boolean expression from a logic diagram, so we have to proceed from the primary input side and go towards the primary output. So, this is the procedure that work progressively from the inputs to the output, adding logic expressions to the output of each gate in turn. So, this is my input A B C. Okay. Now, I find that at the first level there is an inverter here. So, inverter will transform A to A bar. At the next level, if we see, there are two gates, gate number 2 and gate number 3, where gate number 2 is a NOR gate. So, in the NOR gate, one input is A bar, another input is B. So, at this point I am getting the expression A bar NOR B. Okay. So, A bar or B whole bar, whatever way you read it. And then this gate number 3, it has got B and C as two inputs, and this is an AND operation. So, we get a BC as the output. Then finally, at gate number 4, this is a NAND gate. So, you get the NAND of these two inputs. So, A bar plus B whole bar and BC. So, you get the NAND of them. So, Z equal to this expression. So, of course, this can be simplified, but it is not done here. So, you can break down this expression and see what it is turning out to be, but it can be we will see that later. Now, sometimes it is necessary that we are given some logical statement, and from there we need to get the corresponding Boolean circuitry. So, this can be done like this. A typical example has been taken here. So, this exclusive OR gate, so we can write it like this, that output should be true if either of its inputs are true, but not if both inputs are true. As we know, that is the functionality of the XOR gate. So, its output is 1 only when only one of the inputs is equal to 1. So, you can say we can. So, the way we have put this statement, so it is true if either of its inputs are true. So, this is the first part of the statement. So, either of its inputs are true. So, this is the first part of the statement, but we can read it like this. So, if I replace this but by AND, so we can say AND not if both inputs are true. Okay. So, this can be represented like this. So, now you just put the statement like this, that this either of its inputs are true. So, this boils down to A or B. Okay. So, either of its inputs are true. So, this boils down to A or B is true, and not if both inputs are true. So, both inputs are true. So, this part is basically A and B. Okay. So, this is A and B, and this not. So, this not is it is not true. So, this not. Okay. So, this has to be, so A or B should be there, and A and B not should be there. So, A and B not is basically the NAND. So, I can say this, if I join these two, I get a NAND. So, from this I get a NAND of A and B. I get a NAND of A and B. So, that should be there, and then it should be ANDed with A or B. So, this is OR of A B. So, this is the whole expression that I am expecting. So, we can write it like this. So, here what I have written. So, this is first part is A or B, then this AND. So, AND is this AND, and now I have got A and B not. So, A and B not is basically this one. So, this is the NAND gate A and B not. Okay. So, this way we can from a Boolean expression from a logic statement. So, we can try to come to the corresponding Boolean expression. So, that may be done, and if it is difficult, so we can try to draw the corresponding truth table from the Boolean, from the logic expression, from the logic statement, and from there we try to come to the Boolean expression. So, we will see those techniques slowly as we proceed through the course. So, now once we have got the logic function, so we can represent it in the form of gates, like say, so this first of all I need an A or B. So, this OR gate, it has got A and B as input. So, I get here A or B. Then I need a NAND gate. So, to get A B bar. So, this is the NAND gate getting A B bar from A and B, and then finally these two are to be ANDed. So, this is ANDed. So, we get C equal to A plus B dot A B bar. So, this way from the logic statement, so we can so we start with the logic statement, and from there we finally come to the corresponding logic circuit. Okay. So, that can be done. So, as I was telling that sometimes it is easier to get the logic function through some truth table. So, we start with the logic statement, from there we try to draw the truth table, and then the truth table gives us the functionality, and then we try to implement it. So, suppose we have got some logical statement, and from where we get this as the truth table, that is whenever the C being equal to 1, this is equal this. So, we write down all possible combinations of combination of values of A, B and C. So, 0 0 0 to 1 1 1. Out of that we see that in these 3 cases the output is equal to 1. Okay. So, when this A bar, B bar, C, okay, A and B and 0 and C is 1, then output is 1. Then this A, B bar, C, in that case it is equal to 1, and A, B, C bar, this case this is equal to 1. So, if we are trying to get the corresponding logic circuit, then what we should do, from the truth table we should write down the Boolean expression first, and then we try to we realize this Boolean expression by means of logic gates. So, corresponding to this we can say that x equal to A bar, B bar, C plus A B bar, C plus A B, C bar. Of course, I have not done any simplification of the Boolean expression here, that may be done, but I am not going into that, I will come to that later. So, once we have got this Boolean expression, now the process is straightforward. So, first of all at the top level I will need an OR gate, and since there are 3 such terms in this sum of product expression, so I will need a 3 input OR gate. Okay. So, this OR gate is 3 input OR gate. So, it will the first input should correspond to A bar, B bar, C, second input to A B bar, C, and third input to A B C bar. Now, how to get this A bar, B bar, C? For getting A bar, B bar, C, I need a 3 input AND gate, and where A bar should be the first input, B bar should be the second input, and C should be the third input. And for getting A bar, so we complement A. So, getting A bar here, similarly we complement B, we get B bar here. So, this A bar, B bar and C, they are connected to the first gate, first AND gate. Similarly, second AND gate I will realize A, B bar, C. So, this A is connected, this B inverted output B bar is connected, and this C is connected. So, this way we get A, B bar, C, and the third AND gate is A, B, C bar. So, that similarly we get A, B, C bar, and finally, when they are ORed you get this Boolean expression. Fine. So, in this way, so you can start with the truth table, and from the truth table you can realize the corresponding function. So, it may be possible to simplify the logic, that we have seen in our discussion on Boolean algebra, that sometimes it is possible to simplify this sum of product expression or product of sum expression to have lesser number of literals and lesser number of operands. Like it may be that, suppose we have got a Boolean expression like this, x equal to A B C plus A bar B C plus A C plus A C bar. Now, if you try to realize it directly, then what will happen is that you will need a 4 input OR gate like we have it here, and then it should, this 4 inputs should correspond to this these products A B C, A bar B C, A C and A C bar. Now, so you, since you are needing both A and A bar, so you will be needing an inversion of A to get A bar. So, this line A bar line should be connected to this point, whereas the points where you are getting A directly, so can be taken from this point and connected to A. So, you can so this, for the sake of simplicity, the connections are not shown, but what we mean is this line is connected here. Similarly, this line is connected to this A, then this A, okay, then this A, it is connected to all this. So, it is not shown explicitly because that will complicate the diagram. Okay. So, it is they are not shown. So, but this whole expression can be simplified to this B C plus A. Okay. So, you can just do this simplification. So, you can just from the first 2 terms, so you can take B C common, and this is A plus A bar. Similarly, from the next two terms you can take A common. So, it is C plus C bar. So, this B C A plus A bar is equal to 1 and C plus C bar equal to 1. So, the simplified form is B C plus A. So, once you have done this simplification, so you can realize the circuit with much less number of gates. So, you see that I need a 2 input OR gate for ORing this A and B C and a 2 input AND gate for getting this product B C from the inputs B and C. So, that way this Boolean expressions can be simplified, and then the simplified Boolean expression may have much less number of logic gates. So, that is one of the motivation why we should do this logic minimization, because in terms of logic gates, so it will require less number of gates and less number of connections, complexity of the circuit becomes less, and naturally since the number of gates needed is less, so the area then power requirement everything will go down for the resulting circuit. So, next we will be looking into another important concept. Like many times what happens is that if say this is suppose this is a this is an example circuit where we have got a few gates G1, G2, G3 and an inverter, and this A, B, C, D, these are the inputs. So, many a times what happens is we give this A, B, C, D, so they do not have fixed value over the lifetime. Okay. So, they have got different values. So, we just draw some sort of timing diagram. So, they are also known as pulsed waveform. So, this we just try to see when these outputs inputs are changing, like initially A was equal to 1, at time 0 it has become equal to 0, it continues till this time, then it becomes 1 and it continues to be high for this much time, then it again comes down to 0, then it goes like this. So, this way suppose this is the waveform for A, that is every alternate time instant. So, it just toggles its state. Similarly, suppose the input B, so it was initially 0, initially low, then here it goes 1, so it remains high for this much time, then it goes low, then again it remains low for this much time. So, it toggles every 2 time units you can say. So, it is toggling like that. Similarly, C is toggling every 3 time, so 4 time units. So, this is this was initially 0, it becomes 1 here, for 4 time units it remain equal to 1, then it comes down and it goes like this. Similarly, D is D is 0 for this much time, then it goes high and remains high for 2 time units, then comes down and then goes to 0. So, these are the inputs. So, A, B, C, D, these are the inputs. So, these waveforms are given to us. Okay. So, based on that we try to predict what will be the output of the circuit at different time instants. Okay. So, to do that, what do we do is we first see how G1 will look like. So, for getting, so G1, so you see whenever A is equal to 0, so A bar, so this is A bar, this line is A bar, so this is equal to 1. So, or B, so you can understand, so since the OR of these two, so whenever B equal to 1 or A equal to 0, the G1 will be equal to 1. So, you see that whenever B is equal to 1, so this G1 equal to 1. Similarly, whenever B equal to 1, G1 is equal to 1. And also whenever A is equal to 0, G1 is equal to 1. So, A equal to 0, G1 equal to 1, A equal to 0, G1 equal to 1. Similarly, A equal to 0, G1 equal to 1. So, whenever A is equal to 0, like here A equal to 0, G1 equal to 1. So, in this way from this logic circuit, so we can draw the diagram for G1. Similarly, for G2, so G2 is basically OR of C and D. So, whenever C or D, so either of them is equal to 1, G2 output will be equal to 1, otherwise it is 0. So, C is 1 for this much time, so accordingly G2 is 1 for this much time, and then after that say D has become 1. So, from this point onwards, so this is equal to again 1, but till D is equal to 1, and in this part, so both C and D are equal to 0, so it comes down to 0. Similarly, at the beginning both C and D are equal to 0, so G2 remains at 0. So, this way we can find out the status for G2, how it proceeds with time. And finally, the G3 is the end of G1 and G2. So, whenever G1, G2 both are equal to 1, G3 will be equal to 1. So, G1, G2 both are equal to 1 for this much time. So, this G3 is equal to 1. Again for at this time, so G1 and G2 both are equal to 1. So, this is equal to 1, otherwise it remains at 0. So, this way Very often, so we will be drawing these pulsed waveforms for combinational circuit. So, given the input, so we will proceed step by step drawing this pulses pulsed output for each of the gates, and finally, we will reach the primary output, and there we get the overall output for the system. Next, we will be discussing something called universal gate. So, as the name suggests, so universal means you can do you can realize anything using those gates. Okay. So, you can realize any digital circuits using those gates. So, like NAND gates is one of the one such example that can be used for realizing any circuitry, and that is why it is called universal gate. So, they can be used to produce other basic Boolean functions. Basic Boolean functions are, if you look into this sum of product or product of some expressions. So, the basic functions are AND, OR and invert. So, if I have got a gate by which we can generate these three basic functions AND, OR and invert. So, that gate can be used to realize any other function. So, that is why, so we will be calling this AND, OR, NOT as the basic gates and the basic Boolean function. So, this NAND gate can be used for realizing this basic Boolean function. How? So, if you want to get an inverter, okay. So, what you can do, take a 2 input NAND gate and then just short both the inputs and connect the input A, the inverter, the corresponding. So, we are interested to get this inverter. So, our objective is to get an inverter like this. So, this A will be input and A bar will be output. Okay. So, what you do is that you take a NAND gate and then short the two inputs and then apply A at both the, or you can say that you apply A at both the inputs. So, and get A bar as the output. So, we can realize inverter using NAND gate. Then you can also realize this AND gate by using NAND gate, because for realizing AND gate, first of all you do a NAND of A and B. So, here the objective is to get the AND function. So, I will have this AND gate and this A and B are the two inputs. Okay. So, A and B are two inputs and you just do this. First of all, you do a NAND. So, you get A B bar here, and after that use another NAND gate as inverter. So, you get A B. So, you can get this AND function from the NAND. And for getting OR gate, what you do is that with this OR gate, this is slightly tricky. So, we use this De Morgan's theorem actually. So, this A or B, it can be written as A or B whole double bar. So, that way I am taking complement twice. Okay. So, as a result, this will be complementing this will be giving me back this A plus B. Now, if I just apply De Morgan's law on this part, okay, if I apply De Morgan's law on this part, so this will give me A bar dot B bar and this whole bar remains as it is. So, what is happening is that, so this is nothing but NAND of A bar and B bar. So, you take the NAND of A bar and B bar, and for getting A bar from A, you use the one NAND gate as an inverter, and for getting B bar from B, use another NAND gate as inverter. So, that way this whole circuit gives us A plus B. Okay. So, using only NAND gates. Of course, the number of NAND gates needed is more, but that is not a problem. So, if assuming that I have got an infinite supply of NAND gates, so I can realize any function by means of this NAND gates only. So, I do not need any other gate, okay, for realizing the functions. Now, similarly, you can also have this you can also realize this NOR gate using this similar technique, like say so the up to this much, so this is the OR gate, and if you need a NOR gate, so you can just put another NAND gate as an inverter at the end, and that will give you the NOR gate. So, this NOR gate can also be obtained from NAND gate. So, all the gates can be obtained. Similarly, so we have got NOR gate as another universal gate. So, apart from NAND gate, we have got NOR gate as another universal gate. How? So, here also the same thing, like if you are trying to get this inverter A bar from A. So, what you do, apply the same input A to both the inputs of the NOR gate. So, you get A bar as the inverter. If you are trying to get an OR gate, it is quite simple. First of all, you do a NOR of A and B. So, you get A NOR B and then use another NOR gate as an inverter. So, you get A or B. If you are trying to get an AND gate, okay, so then it is slightly tricky. So, you have to apply that De Morgan's theorem. So, basically this A B can be written as A B double bar. So, this is A bar or B bar whole bar, fine. De Morgan's law was this x y bar equal to x bar plus y bar. So, I am just using that formula. So, this A B bar this A B bar I am writing as A bar plus B bar, the upper bar remains as it is. So, what we have is that so here you have got that this is the A bar or this is the A bar or B bar, that NOR gate, A bar NOR B bar, that NOR operation, and for getting A bar from A, so use another NOR gate as inverter, and for getting B bar from B use another NOR gate as inverter. So, that way we can do this thing. So, if you are trying to get a NAND gate, then it is simple. So, you get this AND gate up to this much, and after that you put an inverter, okay. So, another NOR gate as an inverter. So, you get the A B bar. So, this way we can have this universal NOR gate, it can realize any other gates, okay, and or not. Actually, this NAND is not necessary, because if you have to prove that a particular gate can act as universal gate, what you need to show is that it can realize an inverter, it can realize the OR function, it can realize the AND function. So, these are the three things to be shown. So, this is shown as an extra, okay. So, this is not mandatory to show. So, some other combinations, so AND or invert, so other universal gate combination. So, apart from this NAND and NOR, so we do not have any other gate which alone can act as the universal gate. So, but if you take a combination, then it may be possible, like say this one, say AND or invert is definitely AND or invert is definitely one possibility, because this here it is direct. So, AND gate can be realized for realizing AND part, OR gate for the OR part, and the inverter part for the NOT part, NOT operation. So, any Boolean function that you write, say f equal to so f equal to say a b plus c d bar, something like that. So, you can very easily realize using AND or invert gates, that we have already seen. An interesting combination is this XOR and AND. Okay. So, what is the this XOR? So, you see, suppose I have got an XOR gate. So, f equal to A XOR B. So, what is the truth table for this? So, this A B, so when both are 0, 0 1, 1 0 and 1 1. So, this is equal to 0 and this is equal to 0, and these two are equal to 1, fine. Now, you see that if I make this B input forcefully equal to 1, so this B equal to 0 combinations do not come. So, B is made forcefully equal to 1. Then what happens is that if you give A equal to 0, you get a 1 at the output. If you give 1 as an input, you get a 0 as the output. So, this XOR gate, which is like this, A B as 2 inputs and F as the output. Now, if I set this B to be equal to 1, then this is nothing but I have got as if this is an inverter. So, this when A is equal to 1, it behaves as an inverter, as if I have given A here and I have got F, which is equal to A bar. So, in XOR gate, so if you tie one of the inputs to high, so you get an inverter. So, from the XOR gate I can get inverter. So, now if I have got an infinite supply of XOR and AND gate, so I can realize OR gate also. For example, so I have to realize say A or B. Okay. For getting A or B, so I can write it like this. So, A bar dot B bar whole bar, Now, I can for getting this A bar I can use one XOR gate. Okay. So, I can use an XOR gate with one of the input equal to 1. So, A is applied here. So, this is your A bar, and similarly I take another XOR gate with one input as B, other input tied to 1. So, this gives me B bar, and once I have got this A bar and B bar. So, I can take an AND of these two, I take an AND of these two. So, I get here A bar dot B bar, and after that I have to take an I can take an inversion. So, I can take it to another XOR gate. Okay, so, I can do it like this with one of the other input of the XOR gate tied to 1. Okay, so, here you get the F. So, you see ultimately we are getting F equal to this one, A bar B bar whole bar, and that is nothing but A or B. So, this way if I am given an infinite supply of XOR gate and AND gate, I can realize OR function also, and once. So, I have shown you the realization of OR, AND is already there in the set, and from XOR I can get the inverter also. So, this AND or invert, all the three basic gates can be obtained from this set XOR AND. So, naturally XOR AND is an universal set. Similarly, this XOR OR, so this is also an universal set, because in this case OR is already there. So, what is not there is the AND gate. So, if equal to AB. Okay. So, AB if you want to realize, so you can take 2 bars and then you can simplify it as A bar plus B bar whole bar. And now, the same strategy I will follow. I will take one XOR gate to get the invert of A. Okay. So, this is tied 1. So, you get A bar here, and then you take another XOR gate. So, this is your B and 1. So, you get B bar at this point, and then you take OR of these two. Since I have got an infinite supply of OR, so I can use one OR gate here. So, this gives me A bar or B bar, and then I do another inversion by connecting it to another XOR gate with the other input tied to 1. Other input tied to 1. So, here you get F equal to A bar or B bar whole bar, fine. So, this way we can realize this XOR OR, it is also an universal combination. Okay. So, you can find many other universal combinations, so which does not include NAND and NOR gate. Okay. But the fundamental thing, like if you are given say only AND and OR, so only these two, then it is not an universal set, because you cannot do inversion. Similarly, in the XOR family, so with XOR if AND is not given or neither of AND or neither of them are given, then only XOR will not act as an universal set, because in that case you cannot realize all possible basic gates from there. So, whenever we have got a combination of gates that can give us all possible basic functions, so we will call it an universal set. And NAND and NOR gates, they are individually universal gates, and we can have other combinations like AND or invert, XOR AND, XOR OR, like that.